Okay, so now we want to find out, what j minus 1 is when j is j1 plus j2. How do you suppose we find that out? Okay, so this is, what kind of a state is this? The j eigenvalue and the m eigenvalue, they're the same, right? So what kind of state is this?
Maximal.
It's a maximal weight state, right? So if I apply to it a j plus operator, what will happen?
Vanish. The state will go to zero state.
But if I apply to it a j minus operator, what will happen?
The m eigenvalue would be reduced by 1.
So it'll come to this state. So we can find out with this state by just applying our j minus state on this state. As easy as that. Okay, so let's do that. So j minus acting on j. What is j minus? J minus is j1 minus plus j2 minus, right? So it's also acting on jj. But the right hand side, we can write this as j1 minus acting on j1 times j2 plus j2 minus acting on j1 times j2. Okay, so let's look at the left hand side. Okay, so the left hand side is, according to our formula, j minus acting on j is going to be given by j times j plus 1 minus j times j minus 1 square root j minus 1, right? Because this is, these guys satisfy the angular momentum algebra. And what is this? There's a j squared term, and there's a minus j squared term, and then this is going to be simply 2j square root j minus 1. So this is the left hand side. What is the right hand side? The right hand side is the same thing, but j1 applied to this thing, j2 applied to this thing. So if I do this, then the first thing is going to give me 2j1 square root of j1 minus 1. The j2 in that term remains unchanged. The second one will be 2 of j2, j1, and the second term is j2 minus 1. Do you agree? Yes, no, very good. Paruti biscuit. What do you say? Do you guys follow? Can you hear me? Hello?
Yes, sir, we can hear you, I think.
Okay. Well, I was looking for a response, so since I was not getting a response, I was like, okay, did I somehow drop off. So did you follow what I was saying? I applied the same operator on the left side and the right side. And I use the same formula 3 times. If there are any questions, please ask the question, okay? Okay, so if there are no questions, then we can equate left-hand side to the right-hand side. Then the left-hand side is this thing. And the right-hand side is this thing. And there's an equality between them. And then I can divide both sides by square root of 2j. Then I get j minus 1 equal to square root of j1 by j. And then here I get j1 minus 1, j2 plus square root of j2 by j, j1 j2 minus 1. So thus we see that for j equals to j1 plus j2, but for its m value, j1 plus j2 minus 1, we have two ways. There are two states. One is the state where j1 m1 remains j1, but m2 becomes j2 minus 1. And the other one, m1 becomes j1 minus 1, m2 remains j2. And it's a linear combination. Okay, so let me stop there, and I think you should go and review this, and I will finish this up next time. And maybe also, start from a little bit back. But before we leave, are there any questions? Did you find this very difficult or boring?
So apart from the tensor product was a bit problematic for me. I guess I'll have to review that.
Yeah, the tensor product is not supposed to be, the way I presented it is not supposed to be rigorous. I just thought that if I spend time giving a rigorous definition of tensor product, I will never be able to finish angular momentum. So I'd rather give
so by the way, like these states multiplied, like there is a tensor product hidden, like is it
right?
implicit?
Yeah.
Like is the tensor? Yeah. Okay.
Yeah. When in quantum mechanics, we're like, oh, we have two particles. One has a wave function, say psi of x. Another one has a wave function, say phi of, say x1 and phi of x2. What is the combined system? Well, it's just a multiplication of these two, right? We don't bat an eye when we say that. That's exactly a tensor product. That's nothing but a tensor product.
Oh, I see.
That's exactly a tensor product, right? The combined system, say chi x1, x2, is just this, right? So tensor product is nothing but multiplication. Keeping in mind their argument, because now if you want to do, okay, I want to do stuff on this, so I want to say apply the momentum operator. I have to ask you what momentum operator? The momentum operator for the particle 1 or 2, or the total momentum operator. And you say, oh, particle 2, and then okay, then let me just multiply with minus 1 IH d by dx2. Then of course this guy, nothing happens to this guy. So if I'm applying to this, what's happening is this derivative is only acting on this thing, and that's exactly what we're doing with the operators in tensor product. they are just acting on the particular Hilbert space and leaving the other thing, other thing alone. And of course, because P1 is a derivative with respect to x1, P2 is a derivative with respect to x2, and P1 and P2 will commute because they live on different spaces, right?
Now things are quite clear.
So it's just like this familiar thing formalized. Okay, so let me stop here, and I think I will have to start from the beginning, somewhat from the beginning. I will not go through the definition of tensor product, but I will, what I've derived today, I will do that again, okay? And I will also fix your grades today after class.
Sir,
For that.
I missed about 20 minutes of the class due to power outage. Could you give me some references for this stuff?
Yeah, this is all based on the Binney and this is all based on Binney and Skinner.
Oh, okay.
Okay, so that's a very good book. Just read it. I mean, it's completely 100% based on that.